Hello everyone, thank you for attending my talk. My name is Saad and I will be presenting our paper titled Root Cause Analysis for the Deteriorating Bitcoin Network Synchronization. This is a joint work in collaboration with Professor Songqing Chen from George Mason University. Here's a brief outline of my talk. First, I will give a brief background about Bitcoin network synchronization and its deterioration over time. Next, I will present our key contributions, which include measurements and root cause analysis to investigate why synchronization is deteriorating. Then I will discuss approaches to improve network synchronization, followed by conclusion. So what is Bitcoin network synchronization? So network synchronization determines how many nodes have an up-to-date blockchain at any time. In 2013, the Bitcoin network synchronization was strong. There were approximately 3,000 reachable nodes, and when a new block was released, 90% of those nodes would receive a block within 11 seconds. By 2018, the network size had increased to 11,000 reachable nodes, and in our prior work that appeared in ICDCS 2019, we showed that there was a deterioration in synchronization, and we found instances where only 30% of the reachable nodes received a block in 600 seconds. Intuitively, we attributed deteriorating synchronization to the increasing network size. However, recent data from 2019 and 20 contradicts that assumption, where we found that while the network size remained constant, approximately 10,000 nodes, the network synchronization deteriorated from 72% to 62%. Therefore, we concluded that block propagation and network synchronization cannot be solely attributed to the network size. A natural research question then becomes, what other lesser known factors apart from the network size play a role in synchronization? By looking into the Bitcoin network anatomy, we hypothesized that synchronization can be attributed to four factors. Number one, the number of unreachable nodes. Number two, the addressing protocol. Number three, the message relaying protocol. And number four, the network churn. And before I dive into how we analyze each of these factors, I will just briefly overview the Bitcoin network anatomy. The Bitcoin network consists of reachable and unreachable nodes. The reachable nodes establish 10 outgoing connections and accept 115 incoming connections, while the unreachable nodes only establish outgoing connections. Since no two unreachable nodes can directly connect to one another, therefore any information exchange such as transactions or blocks between two unreachable nodes are actually relayed by the reachable nodes. Therefore, reachable nodes play a critical role in provisioning network synchronization. To explore the effect of these four factors on synchronization, we set up a data collection apparatus in which we collected IP addresses of reachable nodes from bit nodes in DNS server database. We then connected to those reachable nodes and exchanged get address messages to collect the IP addresses from their IP tables. In 60 days, we connected to more than 28,000 reachable nodes, and on average, we connected to approximately 8,000 nodes on any given day. Coming to the experiments and key findings, to analyze the impact of unreachable nodes, we first looked into the address message to identify all the unreachable nodes in the Bitcoin network. We found a total of over 600,000 unreachable nodes during the entire measurement study, with approximately 194,000 nodes present in the network at any time. Therefore, we concluded that unreachable nodes are 24 times the number of reachable nodes. As a result, the block traverses more hops than we had earlier anticipated, leading to an increase in the block propagation delay and a decrease in network synchronization. Coming to the experiments and results regarding the addressing protocol, we looked at the percentage of reachable IP addresses relayed in the address message by the reachable nodes to which we connected. And surprisingly, we found that only 14.9% of all IP addresses in all the address messages belong to the reachable nodes. Ideally, this should be 100% because you would ideally want all your outbound connections to be successful, and those would be made to the reachable nodes. However, in all those address messages that we received, only 14.9% of IP addresses in those messages belong to the reachable nodes. Therefore, one can assume that if an outgoing connection of a node drops, its success probability of establishing the next outgoing connection would be low, since the node's IP tables are dominated by unreachable IP. Now coming to the analysis of block relaying protocol, Bitcoin Core implements round-robin block relaying to all connections. Therefore, we analyze the delay incorporated by round-robin relaying to all connections. So we found that on average it takes about 1.39 seconds to relay blocks to all connections. However, in some cases, due to queue in message relaying, the delay can be as high as 17 seconds. And delay in relaying blocks to the reachable nodes definitely affects synchronization, because if reachable nodes receive blocks after a delay, they won't be able to relay it faster to other reachable nodes, which would affect network synchronization. Coming to the network churn, in which we analyze the lifetime of the reachable nodes to determine the network churn. And our findings are as follows. First, we observe that there is a high network churn whereby 8% of the reachable nodes join and leave the network every day. However, the surprising insight was that between 2019 and 2020, the churn among the synchronized nodes had actually doubled, which indicates that perhaps churn is the most dominant factor that has contributed in the last couple of years to the deterioration of synchronization. To sequentially consolidate our insights, first, there is a high network churn in Bitcoin network, due to which synchronized reachable nodes leave the network. And as they depart from the network, there is a decrease in the network out degree. And to fill all the outbound connection slots, when the nodes try to establish new connections, there is a low success rate of outgoing connections, because their IP tables are dominated by unreachable, the IP addresses of unreachable nodes. As a result of this, the network out degree remains low, which naturally affects network synchronization. Coming to the proposed improvements, we recommend the following refinements to the Bitcoin core. First, the addressing protocol needs to be improved, in which only the IP addresses of the reachable nodes present in the try table must be relayed in the address message. Second, block relaying should be prioritized for the unreachable nodes, which are the outgoing connections of a node. Third, based on the average lifetime of the reachable nodes, which we found to be 17 days, a node must remove old IP addresses from the new and tried tables after 17. In conclusion, we explored 4 factors that affect Bitcoin network synchronization. Our study reveals several new insights, including an overwhelming size of unreachable nodes, weaknesses in Bitcoin addressing protocol, and an increase in network churn. And we discovered that increase in churn among the synchronized nodes could be the dominant factor behind deteriorating synchronization. And finally, we proposed 3 refinements to improve the network synchronization. With that, I come to the end of my presentation. Thank you so much for your attention.